All right, let's get started. If you still have not formed your group, sorry?
Is your shirt ironic?
Um,
Because maybe it should be 2 words, not one.
let's talk about this offline. I just got this shirt like 2 days ago, so I haven't had time to process it either. Make sure you email me the name of your group members by just before midnight. I think there are probably still 15 or 20 of you who have not formed your groups. If not, please do it. Remember, if you don't form your group by tonight, then you lose all the points. The next thing up for the mini project is your report, which is due in about a week and a half. Very important for that, before you submit your report, please make sure you form your group on Autolab before you submit, because if you don't, then your group mates will not get any points whatsoever. So if you're okay fighting with your group mates, that's fine by me, but probably not. So make sure you form your group before you submit. And you can submit multiple times till the deadline. How many of you know that we are celebrating our 50th anniversary this coming week? Ooh, all right, so now all of you know. There's a great set of stuff going on starting from this Thursday evening. I highly recommend that you register, use this button to do it. Once you go to the registration website, there will be multiple options. Certain options will ask you to pay. So unless you're dying to pay $450, I would recommend you use the current student and faculty registration option, which is basically free for everything except 2 dinners. So I encourage you to look at it and sign up. You might note that this clashes with classes on Friday, and before you ask the question, no, we still have a class on Friday, and your homework is still due at 11 a.m. on Friday. Okay. All right. Any questions on this? I have to ask your name. Han.
Yeah, I also signed up for the startup weekend, and they're about at the same time. So
you signed up for what?
The startup weekend in the local tech company.
Okay.
And then they're about the same time. So, in your opinion, which one is better?
So the question was, there's another competing event, which one is better? I'll give you my very biased opinion. This is obviously better, right? It's your department. We will have lots of great speakers coming in and talking on Thursday and Friday. And there'll be a bunch of interesting panels on Saturday on like industry versus academia, entrepreneurship and things like that. So go ahead and look up the program. I'm sure you'll find something that interests you.
Okay.
Any other questions? All right, so let's get back to technical stuff. The problem that we were considering last time was the following. I give you as input a graph. Again, remember by default, this is an undirected graph. And you're given some specific vertex S. Okay? And I've changed the problem slightly from what we did last time. Last time I was giving you both a start vertex X and a terminal vertex T, and the question was, were they connected? Now what I want you to do is, instead of checking for a particular T, you output all the vertices T with which the original vertex S is connected. Okay? And it turns out that the BFS algorithm and the DFS algorithm that we'll study actually solve this more general problem. So let's just start off with this more general problem. Any questions on the problem itself? Evan.
Have we shown or stated or proved otherwise that if T1 is connected to S and T2 is connected to S, then T1 and T2 are connected?
Evan's question was, have we argued that if T1 is connected to S and T2 is connected to S, have we proved that T1 is connected to T2? No, but you should do it, and it should be fairly simple to do. But what Evan's pointing out is a nice observation. It's that there's some sort of nice closure property going on. If two vertices are connected to S, they'll connect it to each other too. And so, all right, so the way we're going to solve it is the algorithm that most of you have already seen, is the breadth first search algorithm. The way I'll state it at the beginning might be slightly different from the way you might have seen it before, but it's the same algorithm. So the idea is we're going to build layers of vertices that are connected to S. So S will be our starting point. And here's the algorithm. So we'll have these layers which we are going to denote by L of J, and L0 is the first layer with S in it. Okay? And then what you do is L1 is the set of all vertices that are directly connected to S by an edge. L2 are the vertices that are directly connected by an edge to L1 but are not in L0 or L1. Okay? More generally, let's say we have already constructed L0 to Lj. Then Lj plus 1 is the set of vertices that have not been chosen yet but are connected, this should say connected directly by an edge to some vertex in Lj. Okay? So it's an iterative process. At any point of time, you have, say, L0 to Lj. You look at all the vertices that are not present here, but are connected directly by an edge to the last layer. Okay? And then you try to build the j plus 1th layer. And the algorithm terminates whenever you try to create this new layer and you don't get anything. So if your new layer is empty, that's when you stop. Another interesting kind of concept or data structure that's useful to keep in mind, even though this is not explicitly computed by BFS, is this notion of BFS tree. And the idea is, since you have these layers that you're forming, these layers will be in one level of your tree, and we'll see how you can add edges so that you come up with a tree. Okay? So the basic idea is, if you have a vertex in layer j plus 1, let's call it, say, U. The reason you put it in this layer was because it was connected by an edge to some guy in the previous layer, right? So then just in the BFS tree, just add this edge via which it was discovered. So let's do an example. I believe this example is in the book. And to make things interesting, we'll start off with a graph that is not connected. Okay? So I have vertices 0 to 9. And my start vertex is 1. Okay? So what I'm going to do on the right is build these layers, right? So layer 0 has the start vertex in it. And in this space, you'll see the BFS tree turn up. Okay? So again, this is the initial state of the algorithm. The 0th layer is the start vertex. What should layer 1 have in it? Which node should go into layer 1? Anyone? Alex?
It's layer 1 S or is it the next?
It's S. No, so sorry, I already have L0 having 1, so I want the next layer.
Okay.
2 and 3, right? So we're going to look at all vertices that are connected directly by an edge to 1, which is not 1 itself, right? So in this case, the next two vertices are 2 and 3. That goes into my layer L1. And now note that the reason I put 2 and 3 was because I had this edge. I discovered 2 because of this edge, and I discovered 3 because of this edge. So in my BFS tree, I'm going to add those edges. Okay? Everyone okay so far? Any questions? Okay, so if not, then what should L2 contain? What are the next vertices that should go into the next layer? Alejandro?
4, 5, 7, and 8.
Right, so what you want to look at is all the vertices that are connected by an edge to 2 and 3, or 2 or 3, but are not 1. So remember, we're only looking at vertices that we have not considered yet. So the set of vertices that are connected to 2 and 3 by an edge, but are not 1, 2, or 3, are 4, 5, 7, and 8. Okay? And so we put them in layer 2. And in this case, putting in the edges for 7 and 8 are simple because you discover 7 and 8 from 3. 4 is also obvious because you discovered it from 2. The interesting question now is 5, because you could have discovered it from 2 because of this edge, or from 3 because of this edge. So now you have to make a decision. Any guesses on which one you should pick? Two. All right, if you had said 3, that would be fine too. It doesn't matter. You just have to pick any one of them. Okay? In this case, I picked 2. All right, so that's my layer 2. What would be in layer 3, L3? Stephen? 6. So the only other vertex that's connected by an edge to this layer is 6. Note that 9 and 0 are not connected by any edge to any of in layer 6, in layer 2. So we're going to add 6, and since this was discovered by the edge 5, 6, we're going to add that edge. What's going to happen after this? What would be L4? Stephen? Empty. So there is no vertex that's connected to 6 that's not already there in one of the layers. The only vertex that's connected to 6 is 5, and we already have 5. So in this case, when we try to create L4, the algorithm will be like, well, empty, and so the algorithm stops. Okay? And note that this is the correct behavior, because you should not have 9 or 0 in one of your layers, because they are not connected to 1. Okay? And so, here are the different layers. This is your BFS tree, and you're done with your run for the BFS algorithm. Any questions on the algorithm or its run? How many of you have seen BFS before in terms of this layered business before? Okay, all right, good. How many of you had seen BFS before in terms of queue? Okay, we'll see that too later. Any questions? All right, so now let's do an exercise, which is, note that this graph on the left is not a tree, right? So it has more than n-1 edges. So in particular, there would be edges that are present in this graph but are not present in the tree. So let's add them. Okay. So all the non-tree edges that were present in the original graph but not in this tree are denoted by blue. Do any of you see any interesting pattern among all these edges that I've just added? In particular, pattern in what kind of layers the endpoints are? Evan?
That go up more than one layer or downward.
Right, so as Evan pointed out, either the edges are in the same layer, or they're one layer bottom or one layer up, right? So in particular, if you look at all the non-tree edges, in particular the tree edges also, their endpoints are either in the same layer or in consecutive layers. And it turns out this is not a coincidence, this will always happen. For any graph, for any run of the BFS algorithm, and for any BFS tree that you construct. So what we're going to argue today is, we're going to first argue that every edge is between consecutive layers in the BFS tree. And we still have not actually proved that the BFS is a correct algorithm, i.e. that it will kind of reach all the nodes that are connected to the start vertex S. And the way we're going to prove it is kind of do more work. So we're not just going to argue that just BFS works. We're going to argue that there's potentially like exponentially many possible algorithms, all of which work, of which BFS is a special case. So we're going to argue that BFS works by showing a much larger class works, and later on we'll argue that DFS or depth first search is also a special case. So that way we kill at least 2 birds with 1 stone. Any questions on where we are or what we are trying to prove? All right, so we're going to argue this, that every edge is between consecutive layers. So we're going to prove a proposition. So let T be a BFS tree. One important point to note is for a given graph, and even for a given start vertex S, you could have multiple BFS trees. So if you remember, I forget one of the words, I believe it was 5. It could have gone to either 2 or 3, and depending on which one you pick, you will get different BFS trees. Okay? So you could have multiple BFS trees, but what I'm going to argue holds for all possible BFS trees. So let T be any BFS tree for the graph G. And then we'll say if you have an edge in the original graph G such that, let's say, U is in the layer I and W is in layer J, this necessarily has to mean that if you look at the absolute difference between I and J, it's at most 1. So note that this is equivalent to saying I is either J minus 1, J, or J plus 1. So basically look at the endpoints, and their IDs can only differ by at most 1. Okay, so again, pictorially either in the same layer or between 2 consecutive layers. Any questions on what I'm trying to prove? Okay, let me know if the focus is not good enough. Oh, of course it's not. All right, sorry. So as I mentioned last time, we're going to do the proof. From now on, we're only going to look at proof ideas. And just as a general note, the proof details are in the book. Okay, can you guess what proof strategy we're going to use? Richard?
Well, I have a question about the 3 lines after
Sorry, which one? This one?
it's after the parentheses after 1.
Uh-huh.
No, like before that.
This sign?
Yeah, what is that?
That's equivalent.
What is it?
Equivalent.
How's that different from 2 lines?
So if you go back to mathematical definition of equivalence classes, when 2 classes are equivalent, you use 3 lines instead of 2 lines. 2 lines means they are exactly the same. Equivalence means they are same up to some notion where we consider things to be equivalent. So 1 is equal to 1, and 1 is equivalent to 3 mod 2. All right, go back, review your equivalence classes material from 191, and you should remember what this is. Basically, all right, so if this is confusing, this would work too. It's equivalent. It goes both ways. All right, any guesses on what kind of proof technique we're going to use? Proof by contradiction. Before we go in, I'm going to define another abbreviation that's common. So people write WLOG, sometimes they write it. Have any of you seen this before? No? Okay, that stands for without loss of generality. And what this typically means is we're going to make an assumption which is justified in making, in the sense that we're going to make an assumption, prove everything based on that assumption. And whenever that assumption doesn't hold, we'll argue that it follows trivially from the argument that we've already done. So in particular, here's what we're going to assume. So without loss of generality, assume I is less than or equal to j. And the reason why we can do this is if I is bigger than j, we're just going to switch I and j. Okay? So if not, do argument after switching I and j. So basically what this says is you have I and j, one of them is smaller than the other, less than or equal to the other, call that I. If you have to rename variables, call ji and ij, and you still be fine. Okay? So we're going to only prove this assuming I is less than or equal to j. So for contradiction, we need to assume that this difference is strictly more than 1. Now note that we have argued that j is bigger than I. So if this is the case, then it has to imply that j is strictly bigger than I plus 1, or j is bigger than or equal to I plus 2. Okay? So again, we are saying j is a bigger number, and we are saying that the absolute difference between them has to be more than 1. So you cannot have I and j being I plus 1, it has to be I plus 2 or higher. All right? So the situation is I have my layer L0. At some point, I get my layer I, which has U in it, and J has W in it. So this guy has U. What we do know for a fact by this is J cannot be I plus 1. Right? So maybe somewhere down below you have L of J and you have W. So here's the situation. By assuming that J is strictly bigger than I plus 1, I have the case that I have U in Li and I have W in Lj, and this edge definitely misses Li plus 1. It kind of goes over I plus 1. Okay. And to come up with a contradiction, what we're going to do is, well, let's just go and see what the algorithm would have done when it was creating Li plus 1. Okay. So consider situation when BFS is creating Li plus 1. First thing to note is U is in Li by definition, right? The second thing is W is not in L0 all the way up to Li. Why? Because we have said it's in layer J, which is way down below. So in particular, it cannot be anywhere over here. But note that we definitely know by definition of U and W that that's such an edge. So here's what is the situation. I have an vertex U in the ith layer. I have an edge between U and W. W has not been added to any layer yet. So now if you look at the statement of the algorithm, W will satisfy the condition under which it should be added to Li plus 1. Right? Because it's something that's not added yet and it's connected directly by an edge in Li. Okay? So this implies W satisfies condition to be added in L of I plus 1, and this contradicts the fact that W is in L of J where J is bigger than I plus 1. And so that's it. So talk to your friends for half a minute. Let me know you have any questions. If not, we'll move towards trying to prove the correctness of the breadth first search algorithm. Are there any questions? Richard.
What do you mean by added UM LI?
Sorry?
What do you mean by added UM LI plus 1?
Oh. So if you look at the definition of the BFS algorithm, there's a condition by which you keep on adding vertices to Li plus 1. And the condition is that vertex should not be in layers 0 to Li, and it should be connected by an edge to some vertex in Li. And W satisfies exactly those two constraints. So by definition of the algorithm, it should have been added to the Li plus 1 layer.
What's the word that you added, right?
Sorry?
Is the word you added?
In. Sorry. I have to ask your name. Lloyd.
I and J are the levels, right?
Yep.
And you're saying that it can't be more than one reference, or?
Yep. Yep. So question was, what this is saying is the layers I and J cannot be more than one difference. They can be the same, but they cannot differ by 2 or more. Any other questions? All right, so let's move on. So we're going to define this formally soon, but the set of all vertices that are connected to a vertex S is defined to be the connected component of that vertex. Okay? So if you recall the definition, I said output all vertices that are connected to S. So another way to state the output is given S and a graph G, you need to output the connected component of S in the graph G. And we're going to do, I'm going to show you a simple generic algorithm to solve this problem. And I'm just going to kind of run through this example graph that we had before. And at any point of time, you have this set R that you're ultimately going to output to be the connected component. So you start off with the start vertex being in R. And let's say, you run the algorithm a few times and you have a set R which has a bunch of nodes. Definitely does include the very first guy that you had included. And what you want to find out is if there is an edge that's crossing this set R. What does that mean? That means there is an edge that's outside, a vertex that's outside, a vertex that's inside, and it's connected by an edge. Okay? So at any point of time, you have this set R, and what are you looking for is, are there edges that are kind of sticking out of R? And if there is, and in particular, you identify this vertex V that's not in R and U is in R, you just add that vertex to R, and you continue. Okay? So note that here I'm not specified if you have more than such vertices V, which one do you pick? And what we're going to show is, for the correctness of the algorithm, it doesn't matter as long as you're picking any one. And as a side benefit, we'll show that both BFS and DFS are correct by arguing that this algorithm is correct. And so you basically keep on doing this till you cannot. So as long as there's no, if you're at a point that there's no edge hanging out from this set R, that's when you stop. And the final output, I'm just renaming it R star to distinguish it from the final output versus R, which is something that happens throughout. So, all right, so let's I'm going to rewrite basically the same algorithm that I had earlier. So we initialize this set R to the singleton set that just has the start vertex. And you have a loop while there exists V not in R, U in R, and they're connected by an edge. You add W to R. Okay? And as I said, I'm just going to denote the final output as R star, just to distinguish it from the final thing. Any questions on this algorithm? I have to ask your name. Jared.
I think you switched B and W.
Oh, sorry, thank you. Thanks. Now does this make sense? All right, now does it make sense? All right, I think we are finally good. Okay. So as I said, we have this notion of connected component, which I'm going to define formally, but informally, as I said, basically set of all vertices connected to S. The set of all vertices connected to S in graph G is the connected component. So this is a mathematical term of S. And we'll unimaginatively name it as CC of S. Okay? Thank you. Is there any questions on the definition? Evan.
Wait, so is that denoted by, what does that say?
CC of S
Oh, okay.
for connected component. This, I believe, is not a standard notation. It's something I made up. Is the definition clear? Okay, if it is, then I have a question for you. If I tell you that the graph is connected, i.e. every vertex is connected to each other, what would be the connected component of any given vertex S? Sorry, I forgot your name. You just told Jared, right? Right, so Jared's answer is the entire set V, and that's because why? Well, because I just said the graph is connected. That means every pair of vertices are connected to each other. In particular, if I give you a vertex set S, if I give you a vertex S, every other vertex is going to be connected to that. Right? So in case G is connected, my connected component is going to be the entire set of vertices. So that's a good thing to remember. Note, if G is connected, that implies for all vertices S, the connected component of that vertex is going to be everything. All right, and the theorem that we're going to prove is, again, remember R star is my output, and I'm going to argue that the output is indeed the connected component of it. So if we prove this, then we at least prove the correctness of this explore algorithm. And so what we're going to do next is quickly see why the BFS algorithm is a special case, and then we're going to argue this theorem. So if we argue the theorem and argue that BFS is a special case of explore, then as a corollary, we have also argued that the BFS algorithm is correct. Okay, so I said we're going to do this quickly. It's not that hard to see. So we know that BFS is a special case of explore. Why is that? Well, let's see what happens. Right? So consider the situation at the point when Li plus 1b is being created. So what does the situation look like? I have my original layer L0. I have everything up to layer I that has been constructed. What would be a natural choice of R at this point of time? What are all the set of vertices that BF has explored by the time it has created Li? Right, so it has already explored all the vertices that are in the layers, right? So at this point of time, this is my set R. And what the BFS thing is saying, well, look at the case where there's a W that's outside and it's connected by an H to something which is within U. And add W to Li plus 1. Okay. And you will not only do it for this W, you might do it for W prime that's connected to U prime. Right? What BFS is saying is, I'm going to add all of these guys together. And the way to see that this is a special case of explore is to say, well, let's just put some arbitrary order in which I'm going to add these guys to Li. Right? So once I add W to R, it will become this guy. And then later on, I'm going to add W prime, and that's going to be my R. Right? So BFS is a special case because it says an order in which you're going to add these guys. So in particular, every vertex in a layer kind of goes in together. But you can kind of break that down by saying you just put them in some arbitrary order. Does that make sense? Is everyone okay with the claim that BFS is a special case of the explorer algorithm? Okay. All right, so now we are back to kind of proving this theorem. And so in general, what are we trying to prove here? So here's a general trick. So we want to prove that two sets A and B are equal. Then this statement is logically equivalent to saying A is a subset of B and B is a subset of A. And it just so happens that in most cases, arguing these two statements separately is easier than trying to argue them both together. Okay? So you just argue, you want to prove R star is equal to the connected component of S. So instead of arguing that directly, we're going to say R star is a subset of connected component of S. And we'll also argue that the connected component of S is a subset of R. And if we argue both of them together, then we have proved our theorem. So the first lemma that we want to argue is that the output is a connected component of S, i.e. everything that's included in R star is connected to S. And the second thing we're going to argue is that the connected component of S is a subset of R star, i.e. everything that's connected to S will be output in R star. And note that if we prove both of these, only if we prove both of these, then we have argued that these two sets are actually the same. Okay. So lemmas 1 plus 2 imply the theorem. So before we go into proving these, any questions on why, if we do indeed prove these two lemmas, then we are done? And why that would also imply that the BFS algorithm is correct. Talk to your friends for half a minute, let me know if any questions. If not, we'll go on and prove these two lemmas and be done. Are there any questions? So everyone comfortable with the fact that if we prove lemmas 1 and 2, we are done? Okay. So let's try that. And the way we're going to do it is I'm going to ask you to prove the first lemma as an exercise. And as a hint, you can just prove it by induction. Okay? So we're going to look at the proof idea for lemma 2. Guesses for how we're going to prove it? By contradiction. Yes. So assume that the connected component of S is not contained in this set R star. So what does this mean? This implies there exists a vertex that's connected to S, but it's not in R star. Okay? So this is kind of, actually these two statements are equivalent. And so there has to be some vertex that was connected to S, but for some reason Explore didn't pick up on it. So in particular, this is equivalent to saying so the fact that it's in connected component means that there has to be a path. So there exists a path, SW path P, but W is not in R star. So this is where we came up with by assuming the opposite of what we want to prove. So what does this mean? So I have my set R star, and again remember this is the final output of the Explore algorithm. We do know for a fact that S is in R star because that was the very first line of my algorithm, add S to R star. We also know that we have a vertex W that's outside of R star, and we also know that there is a path. So here's the situation. I know that there is a vertex S in R star, which is connected to another vertex W that is outside of R star. So when you're walking along in this path, you start off with something that's in R star, but ultimately end up outside. So that has to mean there has to be an edge that took you from inside of R star to outside of R star. It's kind of like the following argument. I could say, 10 years back I hated peanut butter, but now I can tolerate it. That means there was some point of time where I transitioned from hating peanut butter to kind of tolerating it. Right? So if you're starting off with one property and ending up with the opposite property, you have to flip at a certain point of time. Okay. All right, so again, I'll just write down in words what I just said. Since P starts off inside R star and ends up outside of R star, there has to exist an edge xy such that x is in R star, but y is not in R star. Note that I'm not saying that this y has to be different from w. It could be w itself, but it need not be. Right? So it is possible that the only time you get out R star is when you finally get to w, or it happens at some early point of time. It doesn't matter. All I need to know, all I needed from this is I have a vertex that's inside of R star x, a vertex y that's outside of R star y, and they're connected by an edge. So, but then Y is a candidate to be added to R. That is, algorithm cannot terminate at that point. So we're saying if there is an edge with X inside and Y outside, the algorithm could not have terminated at that point of time. But the fact that we are saying we have our hands on R star means that we had terminated. Okay? So this implies contradicts algorithm outputs R star and hence has terminated. So talk to your friends, let me know if you have any questions. If not, we have proved the Explorer algorithm is correct. And as a corollary, we have also argued that the BFS algorithm is correct. All right, any question? I have to ask your name. Sorry? Andre? I'm sorry, I can't hear you at all. In the parentheses says since the algorithm has output R star and hence it has terminated. Alex. So Alex's question is why can't we prove lemma 1 by contradiction? You can. I'm not done yet. Okay, any other questions? All right, so as a reminder, the way BFS was running, you build these layers anytime, or you can think of this kind of flooding algorithm going on. Every time a node gets a token, it sends it out to all of its friends. So it's kind of, the reason it's breadth first is because it's spreading everything around. Whereas depth first is the way you will go in the opposite sense, right? You go to the neighbor, then you go to the neighbor of the neighbor, and the neighbor of the neighbor, and so on and so forth. And at some point, you'll get stuck. And then you move back on. Okay. So here is a simple recursive statement of DFS algorithm. You start off, so let's say you're calling the DFS on U. The first thing you do is mark it as explode. You also add this vertex U to the set R that's explode. And for every edge UV, where V is not explode, you recursively call DFS on V. And so we're going to look at this algorithm next time and prove some properties. If any of you want to pick up solutions to homework 2, I have some copies here. Otherwise, I'll see you guys on Wednesday.